Good morning, everybody. We're about to meet. It's the 12th of November, and this is before class, but um, things are really going to start moving in these last couple of weeks. We're losing 2 Thursdays. I'm going to a conference this Thursday, and then Thanksgiving is another Thursday that we'll miss. So I'm probably going to do a couple supplements of sending you some lecture type things and videos. I really want you to watch this one before you start topic 6. So really what we learned in topic 5 is the theoretical setup for confidence intervals and hypothesis tests, which are the next two topics, topic 6 and 7. So when we first started with all this, we really started by sort of saying like, all right, get used to this idea that there's a distribution, a certain amount of the distribution will be within 1 standard deviation, the mean within 2, within 3. And you've been doing that since the beginning of the class, which is the 68, 95, 99.7 rule. So how this applies to topic 5 is to say, if we took, the image that's here is a computer generated, just says, give me 1,000 samples quickly. And the sample is based on, looks like, I believe if I remember right, 0.24 was the theoretical population proportion. And then say, all right, take all these samples of a certain size and take 1,000 of them and tell me what you get. And the simulator is able to spit out and just say, okay, these are all the different samples we got. And what you'll notice is really it never drops below 0.1 or 10%. It never goes above 0.4 or 40%. So what that's really saying, similar to Obama-Romney samples that we did in class, you really should never expect to see values too far from 0.24. And most of the time, you should see values very close to 0.24. So the two standard deviation rules would say 95% of these sample proportions should come back within 2 standard deviations of the mean, which in this case would be 0.24. It follows that we would expect any given sample to have a 95% probability of being within 2 standard deviations of the mean. So the switch that's going to happen in topic 6 is we're not going to say we have infinite theoretical sample proportions. It's going to say we just took one sample and that's all we have. So imagine this red dot just being like, all right, I took a sample. I don't know what it is. I don't know if it's less than the true population proportion, more than the true population proportion. I just have this one sample. So in the image that you see here, there's a 95% chance that if we chose any of these one dots, that it would be within 2 standard deviations of the mean. Because statisticians have studied the normal curve with great precision, it's more accurate to say that we expect 95% of sample proportions to fall within 1.96. Notice that number 1.96 is very close to 2. So the number 2 we've been using as a rounded number. We're going to start using the number 1.96 for that because exactly 95% of the normal curve, the theoretical normal curve is 1.96 standard deviations to the left and right. You can see that right there. This is from StatCrunch. If we type in from negative 1.96 to positive 1.96, notice that that gives us 0.95 right there. And then some other commonly used confidence intervals, which is what we're working towards, is a 90%. You could write a 90% confidence interval, which would just mean you don't have to go quite so far. You don't have to go all the way over to -2 and +2. You can go to 1.645. That's the rounded number we'll use. And if you move out 1.645 standard deviations from the mean, that'll get you to 90% of the data. And if you want a more accurate confidence interval, you can say you can get to 99% of the data by going out 2.576 standard deviations from the mean. Notice that's more than 2, but less than 3. So I'm always going to provide these for you. If you have a test or anything, you'll have printouts with these numbers on them, but you'll very commonly, when writing confidence intervals, you'll use either 1.645, 1.96, or 2.576, depending on whether you're asked to create a 90% confidence interval, a 95% confidence interval, or a 99% confidence interval. Your textbook called these confidence multipliers. Critical values is another term that comes up in other texts. and they call them Z-star. They're called Z-star because they're not technically Z-scores, but they're based on the concept of Z-scores. Like you'd have to theoretically go to Z-scores of 1.645 and negative 1.645 to get to 90%. So this is how it works. We don't know the population proportion. We're going to stop doing that. Suppose you know that the population proportion is this, because in general, you don't. So we take a sample. All we have to work with is our sample proportion, which we call p hat. We then calculate the standard error using p hat times 1 minus p hat over n, take the square root of that. And that's the same formula we've been using, except we've just swapped p for p hat because we don't have a p. We don't know what the population proportion is. So it's kind of like saying, if you don't know what the population proportion is, it's okay to use the sample proportion if that's all you've got. So just to show this, that's equivalent to 1 standard deviation, right? So remember, when you go to like 95%, 90%, you have to move out a number of standard deviations to get to 90% of the data or 95% of the data. So you take that standard error you calculate and multiply by the Z-star, which is depending on your confidence level. And that gives you a term. Oh, sorry. Is this where we were? Yeah. So notice this standard error is the same formula right here. And then you multiply that by Z-star. That gives you your margin of error, which is the thing we've been reading about and seen since the first day, that you'll often come across the margin of error for different studies. And you can write the confidence interval as lower limit, comma, upper limit, which would be the sample proportion minus the margin error to the sample proportion plus the margin of error. And so here's an example. So going back to our Obama-Romney things. So you say you didn't know what the result of the 2012 election is, and you probably didn't. I didn't if I hadn't looked it up. So we'd say, all right, we just have one sample proportion. And let's say we got 28 O's out of 50. So that would be a sample proportion of 0.56. And what this illustration below is supposed to show is like that 0.56, we don't know if that's more than the actual Obama vote or less, or we don't know where that sample proportion would lie in this sampling distribution. Okay, so then going through the math steps of this, we've already calculated the sample proportion. The Z-star for this would be 2.576, and that is because, notice it says write a 99% confidence interval for P. So if you want a 99% confidence interval, you'd use this 2.576. Every time you're doing a 99% confidence interval, you're going to use that value of 2.576. And take that and calculate the standard error by doing p hat times 1 minus p hat over n, take the square root, you do all that, and it gets you about 0.0702. And if we multiplied our standard error by the confidence multiplier, that would be that 0.072 times 2.576, and that gives us about 0.1808. So what that means is we expect our sample proportion to be off by as much as 18%, roughly, give or take 18%. So this last line, I wish it weren't being blocked right now. Wait for that thing to pop back down. This last line, it says confidence interval would be from 56% minus 18% to 56% plus 18%. In other words, we would expect the actual Obama vote to be somewhere between 0.38 and 0.74. And then that's what I'm kind of that illustration is to show the way we create a confidence interval is by putting our sample proportion in the middle and then adding and subtracting 0.18. What does that mean? It means we're 99% confident that the proportion of Obama voters is covered by the interval 0.38, 0.74, as in we're really confident, 99% confident that Barack Obama is going to get somewhere between 0.38 and 0.74, or 38% and 74%. If that strikes you as a very wide window, be like, who cares if you're going to give a range that? That's because our sample size was only 50. It's a very small sample size. So usually your sample size will be more like 1,000. The most general format for confidence intervals is confidence interval equals point estimate plus or minus margin of error. This applies to both categorical and quantitative variables. Notice point estimate, it could be either a sample proportion or a sample mean, and the margin of error might be calculated differently, whether it's a categorical or quantitative variable. So what we're looking at here is confidence interval is p hat plus or minus z star times this equation for standard error when you're using proportions. And then down at the bottom, confidence interval equals x bar plus or minus z star times theta over the square root of n, which means sample mean plus or minus z star times the individual standard deviation divided by the square root of n. Okay, I'm going to stop this video and I'm going to do a different video just to separate proportions and means, just to make it more clear.